Well, in part 4, I explained an important article, and which was very visual, and you could see everything. But this formulation of this article in part 5, it is equivalent to that, but Andrew Martins, the great genius of artificial intelligence that everybody should know, he is really genius. Very great articles, especially in graphical models, in dual decomposition, dependency parsing, many articles, and he has worked with Eric Xing that has explained those dual decompositions and those things very beautifully. And there are also interesting articles, like another article of Andrew Martin is AD3. So let's focus on this one. So you see that everything is the same. First of all, we argue similarly that we say that solving this optimization problem is expensive, and if we don't do all the composition. So even if we use the local polytope and relax it and working on a more relaxed version, still it is not good. That's why we move to the dual decomposition. And in the dual decomposition, your master is always a function of your lambda. And each slave that you give it to a different computer, it can be solved efficiently in the cloud. And it can be solved very fast. And the slaves send messages to the master, and so that all of them converge to some values. So this is the dual decomposition, the subgradient method. We update our master, and we solve those slaves. And for the augmented Lagrangian method, as I said in the previous lecture, I just add an quadratic term, which I always call it residual, because if it goes to 0, then we're done. And we add it for augmented Lagrangian. As I said, we always add this term, although it is nonlinear, but it has good properties. And we solve this problem with the mu and lambda and the dual variables. And we solve the quadratic problem of this form. And this is the algorithm for ADMM. So for larger slaves and multi-valued variables, it becomes more expensive. One possible strategy is to use inexact algorithm that becomes sufficiently accurate. So this can be achieved by warm starting with the solution obtained in the previous iteration. And this strategy can be useful for handling coarser decomposition, in which each factor is a subgraph, such as a chain or a tree. However, unlike the map problem in the dual decomposition subgradient, in which the dynamic programming can be used to compute an exact solution of these special structures, that does not seem possible in QUAP. That, for example, in dependency parsing, we want to know the relationship between the words. And the traditional first-order dependency parsing only talks about first-order relation, which is just the arcs. For example, scoring the arcs from one word to the other word. But we know that if we want to improve dependency parsing accuracies for difficult languages, such as you saw, Turkish and Chinese, we should go to the higher order features. And for example, two higher order features are the sibling one. For example, this is head of this, and this one is head of that one. So it's like a chain. And the grandparent. So this is sibling, and the first example could be grandparent constraint. So, for example, this constraint is the sibling one we want to achieve. So we have two arcs. For this constraint has two arcs. It means that two arcs must be satisfied in order to satisfy this constraint. And as you see that dual decomposition ADMM, the number of iterations, the dual objective is minimized much more rapidly.